All right, so welcome everyone to the Schubert seminar. This is the last Schubert seminar of 2025. Today we're happy to have three graduate students telling us about various interesting things. And we're going to start with Moriah Elkin from Cornell University telling us about open quiver loci, CSM classes, and chain generic pipe dreams. So please take it away, Moriah.
All right, thank you so much. Thank you to the organizers for inviting me. The title of my talk is the outline of my talk. So I'm going to tell you about certain objects called open quiver loci that live in a space of quiver representations. I'm going to tell you about a statistic that I want to compute about these objects that live. The statistic lives in the equivariant cohomology ring of the space of quiver representations. And then I want to tell you how to compute these statistics combinatorially using some new variant of pipe dreams called chain generic pipe dreams. And I want to mention there's a FIPSAC abstract on the archive right now. There should be a full version coming in the next few months. Okay, so let's start with the background space where my open quiver loci live. All of our quivers are going to be equi-oriented type A. So that just means all of the arrows point in the same direction along this type A quiver. So we just have this chain of vertices and arrows. And I'm going to fix a sequence of vector spaces. So I'm going to assign every vertex a vector space to it. This is a fixed sequence. I'm going to pick bases even, call it V. And then within this fixed sequence, I'm going to look at the space of all possible sets of maps between these vector spaces. So I'm associating a map to every arrow in the quiver, and I'm looking at all possible sets of maps. So the space of these is the space of quiver representations for me. And it's this big product of Hom spaces. It's this big product of matrix spaces since I've chosen bases. And it has this important action of this product of general linear groups of each of the vector spaces. And that action is just by change of bases. So for instance, GL of V1 is going to act by left multiplication on Phi1, inverse right multiplication on Phi2, and that is going to have the effect of changing the basis of V1. So this is a standard thing to consider when you're talking about quiver representations. Generally, people will talk about two quiver representations being isomorphic exactly when they're in the same GL orbit in my sense. So I'm not modding out by that sense of isomorphism yet. I'm going to talk about GL equivariant cohomology in a bit. So maybe in some sense that's about morally looking at quiver representations up to isomorphism, but none of that yet. So, okay, we're living in this big product of Hom spaces. What are my main objects here? So to every representation, we can associate a rank array that just records the rank of all of the maps in the quiver and also compositions of maps in the quiver. So for instance, here's a A3 quiver, and here is an example of an element of the space of representations of this quiver. You might notice at this point that I'm using row vectors, so composition works nicely. And let's write down the rank array. So the convention is along the anti-diagonal, we're just going to take the identity map as being the map from vertex I to vertex I. So these ranks are 1, 2, and 1. They're just the dimensions of the vector spaces on those vertices. Below this anti-diagonal, we have both of these maps that I've written down have rank 1, and their composition has rank 0. So that is the rank array associated to this quiver locus. Associated to this representation. And now I can define, maybe the natural thing you would consider is let's look at all of the quiver representations with this particular rank array. So that's going to be the open quiver locus. Fix a rank array, look at all of the quiver representations with that rank array. And I'll mention quickly that these generally aren't actually open except for the one dense one. They're more open in the sense of like open Richardsons, where they're just not closed. So the actually more well-studied thing so far up until now has been the closures, the quiver loci is what they're called. And we have this nice description where they just, you're looking at rank arrays that are less than or equal to your fixed rank array in every entry. So these are my main objects, in particular these. And the question is, what am I going to study about them? And the answer is certain elements of GL equivariant cohomology of this space of quiver representations. So my goal is to find classes in this ring associated to, first of all, the background sort of case is the closed thing, and then also this not necessarily closed thing. So the way we can do this, I should probably start by telling you what this ring is that we're trying to find elements in. To compute this, we can look at the standard torus inside this big product of general linear groups. So just embedding in as diagonal matrices in each of these matrix spaces. And we can look at alphabets of torus weights for each of these tori, and it is a fact that the torus equivariant cohomology ring of a contractible space like Hom is just the polynomial ring with with the torus weights. So each of these is a whole alphabet of weights with the number of variables equal to the dimension of the corresponding vector space. And it's further a fact that this ring that we're looking at is going to inject into this ring as the polynomials that are invariant under commuting each alphabet of variables separately within itself. So the moral of this is that these elements of equivariant cohomology that we're trying to compute are just polynomials in the torus weights. So these are our goals of things that we're going to try and compute about these open quiver loci. For the historical case, the closed things, well, okay, they're GL invariant. Changing bases of vector spaces of the vector spaces is not going to affect the ranks of the maps. So by Poincare duality, these are going to have associated classes in the closed things are going to have associated classes in equivariant cohomology, and these are called quiver polynomials. And these have been pretty well studied historically. Mainly people care about them or have cared about them historically in relation to maps of vector bundles and degeneracy loci of maps of vector bundles since like the 50s. And in 2006, Knutson, Miller, and Shimozono gave not one but four combinatorial positive formulas for these quiver polynomials, in particular one in terms of pipe dreams. And so these quiver polynomials have been fairly well studied. That pipe dream formula has kind of inspired some of these methods that I'm going to talk about in a bit. And I'll mention that I was able to cut down on some cancellation in that pipe dream formula. I'm going to skip it here for time, but that is on the archive if you're interested. Okay, so that was the answer of what class do we associate to the closed things. Just take the associated class. What about these not necessarily closed things? The right thing to consider here is going to be Chern-Schwartz-MacPherson classes. And to tell you what those are, I should define there is a functor from algebraic varieties to abelian groups. That gives you, on a variety, it associates the abelian group of constructible functions on that variety. What are those? They're linear combinations of characteristic functions of constructible sets. Constructible sets are just finite unions of locally closed sets. Essentially, we have a collection of characteristic functions. We can add and subtract them, and that's this abelian group. We also have a notion of push forward of characteristic functions along proper maps. So this is really a covariant functor. And we have another favorite covariant functor from algebraic varieties to abelian groups, and that is homology. So it's a conjecture of Grothendieck and Deligne that was proven by MacPherson in 1974 that we have a natural transformation between the constructible functions functor and homology that satisfies this base case condition for the characteristic function on a smooth variety that you get the total Chern class of the tangent bundle. So really what this natural transformation is it's a map from the set of constructible or the group of constructible functions on your variety to the homology groups of this variety, and in particular to every or any locally closed subvariety, or rather its characteristic function, we can associate an element of homology. That sounds pretty close to what we want. And in fact, due to Emoto in 2006, we can work equivariantly, and we end up with this giving us, I guess, equivariant cohomology class related to locally closed subvarieties by looking at their characteristic functions. And there's this extra business of, instead of working with this inhomogeneous thing, we're going to homogenize by doing this trick of considering this extra torus that does nothing on hom and scales its cotangent fibers. All that really does is we have this extra variable, convention is to call it h bar, and we end up with this Chern-Schwartz-MacPherson class of our open quiver locus. That is a polynomial in here that's homogeneous using h bar to homogenize. And this is the standard abusive notation. Really, this should be the Chern-Schwartz-MacPherson class of this characteristic function. So these are the real things to compute here. And maybe as a hint that these are the right things to compute, is the fact that these classes contain the data of quiver polynomials. We're computing strictly more information. This is a general fact about Chern-Schwartz-MacPherson classes, that if you set h bar to 1 and take the lowest degree terms, you're going to get back the cohomology class of the closure, equivariant cohomology class of the closure. So if we can compute the Chern-Schwartz-MacPherson classes, we know the quiver polynomials. So that's what we're going to be trying to compute here. So the last question to answer is, how can we compute these things? And it's a tiny part of Gabriel's theorem that up to the GL action, or maybe rather up to isomorphism, the indecomposable representations of type A quivers look like laces. So they look like these strings of one-dimensional vector spaces with isomorphisms and zeros everywhere else. And it is a fact that these open quiver loci are exactly the GL orbits. I guess it's maybe clear that they're invariant under the GL action. And to go the other way, it's not so hard to recover, recover this decomposition from a rank array. So what it means to be GL orbits is that each open quiver locus is going to contain exactly one representation that is just a sum of these laces. That looks exactly like that. So here's an example of a rank array and the corresponding multiplicities of these summands of each of these laces. And I think the best way to think about these things is these lacing diagrams due to Abeasis and Delfra in 1985. So we can think about the vertices of these as corresponding to basis vectors. So we have 1 in vertex 0, 2 in vertex 1, 1 in vertex 2. And you can think of the lines as being these summands, these laces. So we have one lace from here to here, one lace from here to here. That corresponds to there being rank 1 maps from 0 to 1 and from 1 to 2. But the composition is going to end up being 0. Okay, so we can use these to index our chain generic pipe dreams that are going to allow us to compute these Chern-Schwartz-MacPherson classes. So what are these things? There's certain variants of pipe dreams. They're not square anymore. So the shape of these things is going to be n+1 rectangles chained from the northeast to the southwest, where the dimensions of the rectangles come from the dimensions of the vector spaces, which are Ri. So for instance, this 0th rectangle being 1 by 2 tells us that at the 0th vertex, we're going to have a one-dimensional vector space. And then at the first vertex, we're going to have a two-dimensional vector space. This one's 2 by 1. So we get the 2. And then we have a one-dimensional vector space. And then we have this last 1 by 0 dimensional rectangle for reasons. Okay, so that's like the background shape. What do the pipes look like? Well, they're going to enter from the right of the diagram on the right sides of rectangles. They're going to leave from the left side of the diagram. If they leave the left, they're going to exit completely. And if they come out the bottom of a rectangle, they're just going to continue due southwest. And we're also only allowing them to do normal pipe dream moves. So they're allowed to move like this, like this, like this, or like this, or like combinations of those things. So for example, we might have a pipe entering this diagram here. Maybe it continues straight. Maybe it bumps down now. Now that it's exiting out the bottom, it continues directly southwest and has to enter into this pipe. And then maybe it continues out directly out of the diagram here and leaves permanently. And now here's how we actually enumerate these chain generic pipe dreams associated to a given rank array. We can construct the lacing diagram from the rank array, and the point is that the chain generic pipe dream should look kind of like the lace array. So the technical way of saying that is the number of pipes that appear in rectangle I and in rectangle J, and every rectangle in between and no other rectangles should be exactly the number of laces from I to J, Sij. And we also have this extra business of coloring pipes based on where they leave the diagram. And we also impose the requirement that same colored pipes cannot cross each other. And this kind of corresponds to if two pipes leave from the same place, it doesn't matter whether they cross or not. If they touch each other, it doesn't matter. They're still going to be chain generic pipe dreams for the same lace array. So if I'm trying to draw a chain generic pipe dream for this lace array or lacing diagram, this pipe works for this first lace because it appears in exactly rectangles 0 and 1 and no other rectangles. And then I need a different color pipe for this second lace. It's going to enter from the right here, and it has to bump down this way because it needs to appear in the second rectangle. So it bumps down, it leaves from the left of the second rectangle, rectangle labeled 2, and it exits permanently that way. And I'll just mention here that there's no rule against things crossing twice. That's because I'm using a formula from Chang-Jan Su in 2018 behind the scenes that doesn't require reduced words. So there's no reduced condition here. Okay, so these are the objects. And we can assign to each chain generic pipe dream a weight in a pretty standard sense for pipe dreams. So just it looks fancy, but it's just row minus column label as usual, associated to any sort of crossing type tile. We get a weight of h bar to homogenize for every bump. We get the sum of these two weights if it's something that can be both in some sense. And if we define our weights this way, this gives us a nice, concise combinatorial formula for the Chern-Schwartz-MacPherson class of an open quiver locus. And the last thing I have is just an example. Here is the set of all three chain generic pipe dreams for this particular lace array or rank array. And it's not so hard to write down the Chern-Schwartz-MacPherson class from this. It's not so hard to write down this list either. But for instance, we get 3 factors of h bar here corresponding to the 3 bump-like tiles, and an a minus b2 is a row minus column label here. And the last thing that I'll say is, like I said, you can recover the quiver polynomial from this by just looking at the coefficient of the highest power of h bar. So here we have a minus b2, and this h bar and this h bar squared give us an h bar cubed coefficient to b2 minus c. Sum those together, you get a minus c. Take my word for it, that is in fact the quiver polynomial for this rank array. All right, that's all I have. Thank you.
Thank you very much. Thank you very much for a beautiful talk. Very nice.